Mhm. Welcome, everyone, to our another webinar hosted by Chemical Engineering Life, titled Safety Design in Process Plant. Welcome to our guest speaker, Mr. Wilfredo Garcia, who is a senior process engineer. Thank you so very much for being here with us today, and also for being the guest speaker. The agenda for the webinar is, in the beginning, we'll start off by a little bit of welcome, introduction to myself and to Mr. Wilfredo. Then I'll walk you through the organization Chemical Engineering Life, telling you a little bit more about what we do, who we are, and what sort of work we do. Then Mr. Wilfredo will once again take the lead and walk you through 4 different case studies of safety design. Then we have 20 minutes reserved for question and answer. So you all will get a chance to ask any questions that you guys may have. And feel free to write it in the chat or unmute yourself when you're asking the question. And then the last 10 minutes are reserved for closing remarks, where I'll tell you more about what to expect after the webinar in regard to the certification and in the evaluation. So first of all, welcome to Mr. Wilfredo. He is a chemical engineer himself with more than 30 years of experience as a process engineer in different projects for different oil and gas industry. He is originally an alumni of Ecole Polytechnique de Montréal, Canada from 1983. And it's not the first time we have Mr. Wilfredo in Chemical Engineering Life. He's actually one of our mentors, currently mentoring 2 different chemical engineering students and a major part of the training program. And Mr. Wilfredo, apart from this, he also has different classes that he offers. So feel free to connect with him on LinkedIn and also get an opportunity to become a student in the classes that he gives. A little bit about myself. Well, my name is Humzaa, and I'm a chemical engineer myself. I graduated from the Technical University of Denmark back in 2020. Since then, I have been working as a quality engineer within a company called Pharma, which is a pharmaceutical within the pharmaceutical sector. My main focus during my master's has been on process design and process engineering, which led me to having 2 different publications within process design with focus on sustainability, biorefinery, and the process analysis. And I am the founder of Chemical Engineering Life. Coming on to the organization, Chemical Engineering Life. Well, the idea is to connect as many chemical engineers as we can from around the globe. A little bit about who we are. We founded the organization back in February 2021. In the beginning, we started off by interviewing different chemical engineers. I reached out to different chemical engineers working in different fields, in different areas, different companies from different countries, asking them questions that a newbie, a new graduate might ask. The idea was simply that we should be able to give an insight into the industrial life of chemical engineers for different graduates, for different students, so that they can get an idea about what to expect when they walk out the university gates. By August 2021, we had interviewed around 35 different chemical engineers, and the same month we launched our website. And all of the interviews can be found on our website. So feel free to visit the website and also look at the interviews. In September 2021, that is when we launched our chemical engineering mentorship program, which is specifically built for chemical engineers. So all the mentors and mentees, they are chemical engineers from different countries. And I will get more into that into the next slide. In March 2022, which is just last month, we launched our webinars. This is the 4th webinar that we are hosting with a guest speaker and many more to come. So once again, if you are interested in joining in signing up for other webinars, feel free to go to our website and stay updated on the upcoming webinars as well. The next month, we are launching our monthly chemical engineering magazine. It's a magazine discussing different topics within chemical engineering, so people can stay updated on chemical engineering industry. So once again, go to our website and remember to subscribe so that you can get an online version at the end of every month. And this is just the beginning. And we like to see there is a lot more on the horizon. So stay updated. And there are a lot more exciting initiatives on the way through which we aim to help different chemical engineering students and graduates. So just a quick note on what we do. So in reality, we are trying to create a community where every single person you meet is a chemical engineer, a chemical engineering of different experience, of different sector of you think of it, and we might have a person within that area. within that community, we try to connect different chemical engineers with each other and try to benefit the students and the graduates by using the experience from industrial and experienced chemical engineers. We do so by our mentorship program, the mentorship program where we connect different industrial engineers with different graduates, different master students, so that they can ask them any questions that they might have regarding anything from CV making to chemical engineering. We have these webinars. Every webinar, we have a guest speaker who is an experienced chemical engineer working in the field or in the research area, so that they can come and give a lecture, and many students and the attendees can get can benefit from their content. And then lastly, like I said, we have these interviews with different chemical engineers. We do an interview every week. So once again, you can go in and read their interviews and see what questions we ask them and what they answer. And you might get an answer to something that you might have been looking for. Coming back to our mentorship program is a biannual program that is conducted for 5 months, twice every year. The first session, it goes from February up until June. The second session goes from August up until December. The session that we are running right now, it is from February 2022 up until June 2022. We currently have around 35 mentees and 42 mentors, and they're all joining us from 16 different countries. We don't like to limit the program to one country or one university or just to simply one industry such as oil and gas or pharmaceutical, but instead it is a very global program, and it's a very open-ended program. So we don't dictate about what you can ask and what you can talk about. And I personally have a meeting with each and every mentee and a mentor that signs up, so that we don't want anyone to be connected with someone on the merely that they are chemical engineers, but in fact, every mentor and mentee are selected based on their own career goals and what they plan to do. So if you would like to work in the cement industry, we try our best to connect you with someone who is working in the cement industry, so that you can ask them questions that might benefit you in your future and for your career planning. So do remember to go to our website, ChemEnggLife.com, and you can sign up for the mentorship program. It is no longer possible to sign up for the current session since it is ending in 2 months, but we highly recommend that you sign up for the next session that we will be starting off in August, for which we already have started the interviewing phase. So if you sign up, you'll be called in for a call within a week, and we can have an interview to talk about your career goals and what you plan to achieve out of the program. Lastly, on our website, we have a free membership as well. The idea for the free membership is so that people can sign up and we can create a community so that people can connect within the website with each other as well, out of the mentorship program and the webinar area. Like I said, it is a free membership, so you don't have to pay anything, but you do get a lot out of it. So go to our website and do sign up today for free member. And if you are a member, you are the first one who gets to know when there's an upcoming webinar or if there is a new initiative. And that is all from my side about Chemical Engineering Life. So Mr. Wilfredo, you can take the lead now.
Okay. So, well, good morning for me. Good afternoon or good night for anyone else. Welcome to this workshop. It's called case studies because this is, let's say, situation that I have faced during my career on projects and in plant operation. So as an introduction, so we as a process engineer, so one of our role is to design safe and operable process plants. So during the design, so we have to be aware of this, okay? Because it's one of our role and responsibilities as process engineers. However, during the project development or during the plant operation, so there are situations that are, let's say, most of the time are given because of pressure that the project management has from the client or from the plant owner to get this plant in operation very quick. So, but us as a process engineer, so we need to be aware of what is the kind of decision they are taking that are not affecting the safety of the plant. Okay, because the plant can be still in operation, however, so we need to be aware of the safety, because the safety is a very big concern for the process plants. And then the safer the plant, so the happy that the owner or the client will be. So we need to be very careful. I insist a lot of things in this because most of the time the people forget about safety. Because we want this project to be run or to be ended in a very quick time, but most of the times the people forget about this topic. The process safety management is mostly not forgotten, just leave it away. So in this case, so can I scroll down, Humzaa?
Sorry, yes, sorry, here you go.
I just selected, well, because of a matter of time, I just selected 4 cases that I have encountered during design or during plant operation. I have several, I have a lot of cases that I have faced, and then I have been, let's say, well, it's like fighting with the project management to convince them to don't do this, or fighting with the plant operators to do this way. However, most of the time, so we are late. In this case, the case is already in place, and then we have to take solutions. And then when they need solutions, they come to us as process engineer to give a quick solution to the problem they have faced. So the first case that is here is the Humzaa cryogenic complex. Is a complex that is so I cannot scroll down, Humzaa, please. Next. So the Humzaa cryogenic complex, so it's a process plant that has been built to process NGL, so natural gas liquid. The natural gas liquid is being generated for an natural gas processing plant upstream of this. It's called Santa Barbara Gas Processing Plant. They take the natural gas, they dehydrate, they take all the treatment for the process gas plant, and they extract the NGL with a maximum 2% of ethane that is being fed to this Humzaa cryogenic complex that I was working in this project. These trains that you see here, train A, B, and C. So the train A and B, they were built to process 35,000 barrels per day. And then the first time we get into this project, so was to upgrade this train A and B from 35 to 50 to process with from 35 to 50,000 barrels per day. Okay, and then in this complex, so they receive the NGL with a maximum 2% of ethane. This NGL is reprocessing. We have so this plant has several distillation columns to recover propane, N-butane, isobutane, N-pentane, and gasoline. So this is the main products they are interested to process is propane, normal, and isobutane. Those are the main products they commercialize in these trains. So the first project I worked with them was to upgrade the train A and the train B from 35 to 50,000 barrels per day. Okay, however, so this is the part of gas processing, but we have to see what happened point of view process safety management, because any of this train has its own flare system. So there is a knockout drum here that I didn't show it because it's not necessary for this case study. I just showed the flare header and the flare itself in that case. So any train has its dedicated flare. Flare for train A, flare for train B. After we finished and completed the upgraded project from 35 to 50,000 barrels per day, the demand on propane and and butanes was still increasing, and they introduced another train of processing train in Santa Barbara field that allowed for this plant to include another 50,000 barrels per day train, NGL processing train. It was called Train C. Okay. However, this Train C now has its own flare system, correct? And when we run the study of capacity of the flare A and B, so we noticed that the Train C cannot be incorporated in one flare, but we incorporated in a couple. So we split the relief header in two, let's say, to vent the gases to both flares, okay? But the problem was not there. The problem was not capacity. This flare A and B, when we study the several scenarios on the maximum flow rate at the 3 trains at the same time, so the flares still have got capacity to process these cases. However, the problem in here was the connection. How do we interconnect this train C into these two flares? So at the beginning of the project, so we didn't focus on how to do it. We just say what we want to do with this flare header from the train C, and then the connection has been done in that way. Okay, we have this header that is there and it's feeding. Very simple. We split in flare A and flare B. This was okay. It has been built. The piping group has done its job, etc. However, when we were during the commissioning, so prior to start of the plant, so we test everything, and then when we try to test how was the behavior of this connection there, so we introduced one potential venting that's similar to the flare capacity. And then what happened? When this system went in operation, okay, for test the venting, and then all the flow go to the flare B. So all the flow go that way, okay? And then what happened that in that place, so that effect generate a vacuum in that section. And then what happened that the flame of the flare A was tense. So we noticed that. We were in the plant testing this, and then suddenly we didn't see the flame of the flare A. Because here, the flow rate was flowing that way and generate a vacuum there. Okay, this was a problem of connection. And then we needed to do something very quick because we were in commissioning that plant. And then we have to run a very quick study. So let's say dynamic hydraulic study to find a solution for this connection to avoid, so to get a proper distribution of the flow coming from that flare header. And then we run some study, and then we got the conclusion that the best, well, it was not a 50-50 distribution that we got there with that arrangement, but this was the best solution that we could give to that, let's say, distribution, and to avoid that vacuum effect in that connection. And then the connection was to include one, so to extend the header and to include something to stop the flow rate coming from there, okay? Because all of you remember the Newton law that if something is moving in one direction, it will not stop. It will try to continue moving in that direction. And this happened as well when we are dealing with fluid flow. We introduce something to stop, to try to stop the flow in that direction, and then to let's say to obligate the flow to go that way, and then to split in something like I don't remember the angle we have there, something like 60 degrees or 120. I don't remember what was the arrangement on this, but this is the best arrangement we give to this flow distribution. And then when we test it again, so the flare A maintained its flame. That was the purpose of this study. Okay, the distribution, as I say, was not 50-50 as we wanted. However, so the distribution was something by 52-48, something like that. Okay, but the purpose of this, to introduce this change, was to get a better flow distribution of the flow. Okay, and to avoid this, and then this is one thing that I bring this case study to this webinar because we as a process engineer, so we have to take care of this very early. Don't wait until the commissioning phase or during the detailed design phase to run this kind of studies in case that we have it in our project. This is the purpose of this, to present this case study. So don't wait until it is too late. As I say always during the project and during the life, when the water is at your legs, so we are flooding. Don't wait until the water is there to say that we are flooding. Okay, so take action very early in the stage of the project to avoid this, because we have to rework. We have to do a rework in that project, and then we have to do it very quick because we were, let's say, handing over the plant to the owner. And then so it's during commissioning that we see this. We didn't, so nobody see that this arrangement will cause that problem during the design. And don't forget something. We as a process engineer, we deal with a PNID. So in the PNID, we show this. However, it's the piping designer that make the design. And then when the piping designer is making the design, it's very important for us to get participation in that particular design, because this is something that is relating to process safety management. And then if we go into the 3D model, if we participate in the 3D model review, it is very important for us as a process engineer to participate in those model reviews. Even if you are saying to don't participate, please talk to your project management, to the project manager, to be there. Because most of the time, the piping group make the best arrangement for them. And then if we see there, so we have additional costs because you have additional material to be introduced in that arrangement rather to use that arrangement. And then so it's remember that in projects we have a triangle. All the projects is managed as a triangle, that you have cost, you have time or schedule, and you have quality at the other extreme. And then these three variables are in equilibrium. Anything you do, so this triangle will move. Somebody will pay the price. Okay, so most of the time we are under pressure during project, but remember, we as a process engineer, we have to do the thing in a good mood. So, and then everything related to safety, please put the eye on safety. Don't just say that I have a process simulation, that everything is fine, that I have got the number, my height and material balance is okay, because this is okay. This is the normal way to do project. However, when we go to the process safety management, so please open your eyes. Okay. Yeah, let's move to the second one. That is the other case study that is in the same cryogenic complex. But in this case, they wanted to operate this plant with the NGL with ethane and the NGL without ethane. That is the case before. So please, Humzaa, the next one. And then the next one, we have the same situation. So already we have these 3 trains in operation with the solution in there for the interconnection. And they wanted to introduce the ethanizer unit. So they say to bring NGL with more ethane and then to process the ethane in that complex as well. Okay, point of view project, it was very good. So we have area to introduce all the plant. So we have area for tankage, we have area for refrigerator, we have area for the refrigeration plant, etc. Point of view process, everything was fine. However, point of view safety management, it was a problem because the owner of the plant, they wanted to use the same flare system that is already installed. And this is logic because it's a matter of cost. So if we already have flaring facilities in the process plant, so I don't have to invest in a new flare. So if you see the situation from this point of view, so it was very easy because it's a matter of cost. However, you were implying of safety. And the reason is very easy. When, well, if we see the material of construction, the material of construction from the the ethanizer unit is mostly stainless steel. And the existing flare and the material of construction of these 3 trains is carbon steel, mainly carbon steel because we don't face lower temperature. The carbon steel point of view resistance and stress is very good down to -20 degrees Fahrenheit. And the stainless steel is very good to an ultra low up to -150 and lower temperature, talking about cryogenic conditions. However, when we start to look at this, so in this time, we learned the lesson from the previous exercise. We say, no, we will not see this at the latest phase of the project. Let's take it early. What happened? We run exercises of the pressuring, the compounds that we have there. Okay, and then for these 3 trains, mainly we have the lighter product that you have in there is propane. When you depressurize the propane to atmospheric pressure, because this and the flare is close to atmospheric pressure operation, so we got 29 to 30 degrees Fahrenheit when we run this exercise. However, when we depressure the lighter stream here, this is the ethane, so the resulting temperature is far below -20. So with this very cold temperature, so this carbon steel material will fail, point of view mechanical, so material selection. So the carbon steel will not withstand one depressuring or one flare release or one vent release from the ethanizer plant. And this creates a problem, a big problem, and a big discussion. So the project management was angry with us. The owner of the plant also was angry with us, saying, well, what is the problem? So if you want to run a safe plant, as we as a process engineer will do, so you have to install a dedicated stainless steel flare system for your ethane plant. You want an ethane at the ethanizer unit in your complex, you need to invest in a new flat. That now it's costing money. That this money they didn't estimate it when they get this proposal. Okay, so they needed to introduce a new budget into the management of the owner of the plant, so to be approved prior to introduce that, to include a stainless steel flare system. And then we needed to convince everyone, starting by our process manager, because they wanted to run this project very fast, because it was very easy, because the plant was already, say, the size of the equipment was already there, because they picked one train from the Santa Barbara extraction plant, the same size, they put it in here with the same capacity, 50 million barrels per day. Okay, the same capacity, no problem with this. But however, we have this constraint point of view, process safety management. And then at that time, everybody insisted that we have to do that. And then we as a process engineer, we say, okay. And then even the owner of the plant, they tell us, no, this plant will never be depressurized. And when we say, what? That this plant will never be depressurized at the level of pressure this plant is in operation? Okay, if you want this plant to don't be depressurized, please let's write one letter. So you submit a letter to us that the depressuring of this plant will be in your hands, and then the failure of the carbon steel will never happen. Please write this to us for us as a process engineer to be free of warranty or responsibility of this, because we didn't want to be responsible for something that we know that in the future will happen, because sometimes this plant will need to be depressurized. So whatever the situation is, you cannot say, no, I will not do it. No, this will happen. Okay, fortunately, this project didn't go further, and then this unit has not been installed in that plant. Fortunately for that plant, so this project was put down. But otherwise, so there will be a big safety problem they will introduce into that complex. But it's as I say, so sometimes people don't understand. People is thinking about money, and they forget that in any project, even in your life as well, so you have another two variable, that is quality and schedule. So you try to earn money, so you need to invest. It will take more time, or it will take quality, and then the safety is in gaming here. And then when we are talking about safety, forget about the rest of the variable, my friend, because it can lead to a very, very, very big problem. Can you imagine that this material fails for any reason, and then the carbon steel crack, and then you have a leak of this light products in that plant? So you cannot imagine the emergency or the problem that we have in this. So this is another lesson we learned in this project, that is dealing with material selection. Okay, so if any of you are working with cryogenic systems, for example, LNG production, please be aware about the material selection, because I have another case study for one LNG plant, but I see that I will have no time to present it in this way, in this today. I prefer, well, maybe in another webinar we will talk about that, or if we speak in LinkedIn or in another communication, I will let you know what happened with that plan. And in another cases, that are not only regarding design, but plant in operation. Can we move to the next one,
Yes.
Humzaa, please? The next one is, well, it's called flare knockout drum liquid carryover. In fact, this is what happened. So please do this sketch to explain what is going on there. So we have been called to run a study for the flare systems because there were several systems for the El Palito refinery in Venezuela. Okay, they say that they have a big fire in the API separator because they have a liquid carryover from the main knockout drum. Okay, this main knockout drum is linked to the flare header from the process plants in the refinery. Okay, but they have maybe 5 or 6 relief systems going to the ground flare as well, but there are several another plants. For example, they have an aromatic plant that they wanted to segregate from that stream. They have an oxygenated plants that they want to segregate as well, and then they have several flare system going into the same ground flare. So the ground flare has a very, very, very high capacity. However, the problem was with this system in particular because they have one emergency in the refinery plants, and then when this peak gas flow rate went into that knockout drum, and then this secondary knockout drum is very small compared to this. So they have, let's say, liquid there burning. Okay, they don't have gas, they have liquid bullets burning in there, and then the wind direction is that way, and then all these firing balls, they drop into the API separator, and they have a big fire in that area. This is the reason they say they wanted for us to run a study to check the capacity of the flare system. And then it's one study we did. So we pick information from every relief or every pressure safety valve and pressure relief valve in the plant. We made the analysis for any of these systems. For the header, we noticed that in some header require to be interconnected, as we did that before for the train A and B, because the capacity was not the capacity. The problem was back pressure for the pressure safety valve that was very high. They were selected, for example, conventional valve, and then for the back safety, for the back pressure, they required to be changed to a pilot valve, but it was not the case. They don't want to do this, so we need to interconnect some flare header to, let's say, to minimize the back pressure. For another case, for in this case, we check the capacity of this knockout drum, and then we say, okay, according to the normal operation of the plant, and then what we've got, the information we got from field regarding the liquids coming into this flare, and then the liquids that are, let's say, condensing during the flare release. So this main knockout drum was okay, and then this is the conclusion we have. So we have no problem with the flare knockout drum, so it has enough capacity to manage the liquid that is expected to be here, and then to manage with the maximum flow rate that is expected to be here. Because remember that in the main knockout drum, normally you have no liquid. Okay, when we have a release from a pressure safety valve, this stream is mostly gas, so we have few liquids. And then just to size this KOT, so we specify one volume of liquid there, and then you install here a pump that start and stop. So it's an on-off pump. When it reach a maximum level, start. When it reach a minimum level, stop. And then normally these pumps here have maybe a 50 or 100 gallon per minute capacity. So we are not talking about big pumps in this, and the operation is on-off because you don't expect liquid to come. So a huge quantity of liquid to come with these streams during the relief head. However, when we were there in field, looking for information, so we have got for some operators what was the real cost. So this is another lesson that we have to learn for all the studies. We have to look for the root cause of the problem, not to deal with the consequence, because we already know the consequence was that you have liquid in there, a burning liquid that causes a fire. But however, what was the root cause of this? And the root cause is one of the operators tell us that they have to let's say to blow down the alkylation plant in the refinery, and they don't have any tank to allocate that volume. And then somebody came with a big idea, because this main knockout drum is a very huge pressure vessel, looks like a horizontal tank. So you see the side, you will drop back because it's quite big. And somebody say, okay, as the fact that the flare knockout drum is never on use, so we can allocate this volume temporarily in that drum. What happened? They bypass the operation of the pump, and they include that volume, that extra volume of liquid, and then they went higher than the maximum liquid level, because it was a temporary solution while they solved the problem at the alkylation plant. But what happened? That there is somebody that his name is Murphy, and the Murphy law, so say something that expect the unexpected. So they never expected that they have an emergency there. They have an emergency, a huge flow rate from here, and then this part of this excess liquid was carried over to that system. And that was the real cause that generate the fire there. But of course, they didn't, during the contract of the study, they didn't tell us that, what was the real cause. But you know, sometimes, so the root cause is known. When you start to run investigations, so you can find the root cause. That is one of the important issues that we as a process engineer have to work as well. So not to deal with the consequence, go to the root cause. Because if we solve the root cause, so the consequence will disappear automatically. These things happens in any case in process plant. So when we have bottlenecks, when we have, yesterday, Mr. Henry was talking about optimization. And then optimization as well, you have a root cause over there. So what do you want? Optimize a plant, but for what? What is the purpose? What is the reason? So you need to go for the root cause to get the consequence. In this case, was like this. And in these cases, that the mostly the owner of the plant is tackling the consequence. But okay, what was causing that consequence? Because when we run the analysis for all the system, we say, okay, so we don't expect liquid carryover according to the capacities we are managing and the size of this drum. So there will not be liquid carry over. However, when they do crazy things, so you will get crazy consequences. Okay, and then don't forget that Mr. Murphy says something that is very clear and very real. Okay, if anything can go wrong, it will, is what he said. And then what we have to do, point of view, process safety management, is to get rid of that principle of Murphy and to think with our head. We think with looking for the root cause, using our intellect. So using the principle that we learn at the university. However, don't get pushed by pressure, because anytime we are in plant operation or in project development, we have a lot of pressure because everybody wants everything to be solved in less time and with low cost. And then when you do that, the quality of the project will go down and the safety of the plant will be in game. Okay, let's go to the another, please, Humzaa. In this case, as well, we will call for to run a study, a safety study for the Muscar gas plant, the first system. Go on, please. And then, well, I will not explain too much what they do in that plant or whatever. It's very important to know. So this Muscar is a very old gas plant in Venezuela, and they don't process natural gas. Let's say they use a treat the natural gas, so they dehydrate the gas, they sweet the gas, they control the dew point of this natural gas for transportation. Basically, is what they do in that plant, and already they have recompression section to re-inject the gas at very high pressure to produce crude oil. Okay, this is what they do in this plant. And in fact, a long time ago, maybe in the year 40, 50, the gas processing was not interesting, because the interest was to produce crude oil, because the crude oil was the source of energy. And in countries as my country, Venezuela, that we are oil producers, so the investment was to export crude oil to get the money. And then the gas was not of interest. Now the gas became interesting from the years 60, 70 and on. But before, so they don't mind with the gas plant. And then thinking with that way, so they make as well crazy design for the gas plant. And then during that study that we run, they call us because they have the existing flare knockout drum explodes. They have an explosion of the flare knockout drum, and they didn't know why. What was the reason? And they start to take measures upstream there. They start to install a restrictionography. They start to check what is the venting, the normal venting operation. So to, you know, they start to look a little bit what was going on. But again, they were tackling the consequence. They didn't go into the root cause. When we got in that plant, so we tried to understand what was going on, and then this is what we found. That the main flare header was underground. From the release of header, so the main flare header was underground, and then go up to the flare knockout drum, and then it went underground again to the flare. Okay, and then what happened when you have gas underground? It will condense, because normally this line, this pipeline, need to free draining to the flare knockout drum, just to avoid accumulation of condensate. Same thing with this line there. This line need to be need to free draining to the flare knockout drum. Otherwise, you have liquid accumulation in there and liquid accumulation in there. So what really happened? That there were a huge release of gases, and then you have a plug of liquid flowing that way, that this knockout drum couldn't manage the force and the impact of that plug and then the flare. And then you have another bottlenecking here, because this line as well was plugged on liquid. And then what happened? That the flare knockout drum couldn't withstand the pressure, and it explodes. Because remember, this flare knockout drum, normally the design pressure is 50 psi. So it's no more than that, because this is supposed to operate at atmospheric pressure. So you have atmospheric pressure at the flare, and maybe we put 5 to 10 psi for this the operation of this flare knockout drum. So this system operates at low pressure, in fact. And then, so what we found is that the most probable cause for this to explode is that you have a plug of liquid in there that has been pushed for a very high flow of gas, and then the flare knockout drum couldn't withstand it with that pressure. And then what the recommendation of this study is say, okay, so what you have to do is to to install a new flare header. Now, not on the ground, but above ground, draining free to the flare knockout drum. And then we have to do something in here as well. So you have to elevate your flare. You have no choice. To elevate your flare to allow this line to be free draining to this, because you don't have. So in this kind of system, a pocket is not allowed. But however, as I explained you, so in the year this plant has been built, so they were not aware of the gas, so they didn't care. However, during the development of this plant, now the gas become interesting. So they introduced the hydration, they introduced gas. They wanted to introduce here NGL recovery. They want to introduce more things, but they didn't solve this problem at that time. And this is the consequence they have. Okay, so here in this case study I presented, so it's most cases for us to use what the process engineer, what is our role. So to design safe and operable plants, and sorry, if the plant is in operation, and this one, at the case of El Palito, so we have to solve. So to go into the root cause and to solve the problem with the root cause, using our common sense, using our intellect, and using our role as process engineer. But don't think it is too easy, okay? Because we have a lot of, I don't call constraints, I will have a lot of resistance, because most of the resistance are the operator. The operator, so they don't want to change anything in the plant. They want it to produce, and they don't think, most of the time, they don't think about change. Okay, this is the kind of people we need to be firm. We need to be very hard. We need to be real. We need to let these people, operator and project manager, most of the time the client or the process plant owner, to let them know that process safety management is very interesting for the plant operation. Okay, for the moment, this is all I have to say. I don't know if I got on time or not, because as I told my mentees, so I speak too much, because I have a lot of things that has happened during my year of experience.
Oh,
Okay.
you made it just in time. So that was completely perfect. Thank you, Mr. Wilfredo. Then now, so now is the question and answer time, and feel free to write your question in your chat if you want, or you can also unmute yourself if you would like to ask questions.
Hi, sir. Hello.
Yes. Hello.
Yes,
Go
sir.
ahead.
Yeah, so I have one question regarding this Muscar air gas plant flare. So, as we saw, the flare header was going from underground originally. Why was it so, sir? Why they made it go through underground? Like, usually we don't see that, right?
In which system?
Muscar gas plant flare.
You mean the one of Muscar plant?
Yeah, right.
Yes.
I will start. There we go.
So why was that flare header was designed to go from the underground and not from the overhead above the ground?
No, because as I told you, so it's an old plant. They didn't care about that, and then they built the plant like this. If you go to field, well, the old fields, let's say, you will find a lot of underground pipelines, because this is the easy way they found to build process plants. However, this is the thing that we found, and then the recommendation was to get rid of this underground plant and to install a new flare header above ground with free draining to the flare knockout drum, as it should be.
Okay, thank you, sir. Thank you.
Okay.
Thank you.
So my next question is the one where you said about flare KOD liquid carryover.
In which one?
Flare KOD liquid carryover.
The liquid carryover. Go back.
Yeah.
Okay. What is the question about there?
Was it possible to install a U piece there between main KOD or secondary KOD and between secondary KOD and ground flare, so that whatever liquid was carryover was happening there, that can get settled down?
Yes, but as this system has been sized, okay, has been designed, so this main knockout drum is the one that will receive all the liquid.
Right.
This secondary KOD is to, let's say, to receive the potential condensing hydrocarbon from this line there and from this line there. That's the reason why this secondary knockout drum is in a pit. Okay, as you see there, so this represents a pit. It is below ground, and this pipeline in here is free draining back there. Okay, to avoid liquid in this in the ground flare. However, the liquid carryover was for another reason, because when we run the evaluation of the flare knockout drum for this one, for any of the flare knockout drum in the plant, so we haven't found any problem with the liquid carryover, because the drums were or was or are, because they are already installed and in operation, big enough to manage any condensation liquid. And then the pumping system there was big enough as well to take that, to control that quantity of liquid in those knockout drums.
Okay. Got it. Thank you, sir.
However, your question is very interesting.
Yeah.
This is another case study I have got in another plant during design, because during design in that project, it was a ground flare as well. However, this secondary knockout drum was not there. Okay, and then they have the main knockout drum that was elevated, and this line go like this to the ground flare. And I say, perfect. So I like that. I like this system. Tell me how we get rid of condensation in that pipeline to where we will send it. So who will collect any condensation in this pipeline if this knockout drum is at a higher elevation than your ground flare? And then I let use that question to the management, to the project management. So let me know what we will do with this, because this is a big problem. Unfortunately, I left that project before the end because I don't know what was the solution, the final solution for that, because they didn't want any pit in that project. Say, okay, they didn't want elevated flare, they didn't want to build pits for another drum. I say, okay, but now we have a problem. How we sort out that problem? But I never got the answer because I left the project.
Perfect. Thank you, Mr. Wilfredo.
Okay,
we have
sir,
another
thank you.
question. Thank you. Then we have another question that why do we put flare system instead of refrigeration cycle to condense all the vapors that are coming from the source instead of wasting them in the flare system?
Well, this recovery system has been introduced in the latest 90s. So it didn't exist before. It's a good question. So nowadays, most of the owners of plants are thinking to recover the most of the liquid for the flare gas, because we know that the flare gas is a rich flame, so you can get a benefit for that flare gas. But remember that we as well, so we will have to how you say, to invest in this recovery plant that most of the owners don't want it. So the best idea is if you are dealing with a new plant, or you are dealing with an old plant, but you are working on revamp plans. So try to introduce that idea during the evaluation of the cost of the project. Don't do it after, so do it before. When we are discussing the scope of the project, so to introduce that idea, to be so to try to get one approval from the owner of the plant, because at the end of the day, it's money, because it's the cost. I have seen this system as a recovery, but not in flare system yet. I have seen it in papers, in magazines, but myself, I have not seen it in a plant in operation. I have seen these recovery gases in another plant, for example, when the loading or uploading chips with light products as methane or propane. So you have a gas recovery system over there with refrigeration. But I have not seen one system in operation for flare yet. Okay.
Mm-hmm. Perfect. Thank you, Mr. Wilfredo. Are there any other questions? Please feel free to unmute yourself or write them in the chat.
I have one more question, sir. So what was the criteria for bifurcating in the first case study?
Sorry, what was the criteria for?
bifurcating that flow rate for train C.
So you mean this?
Yeah, right. Flare C, flare
No,
C.
it's not forgetting. I think that it's more a lack of experience
Okay.
dealing with this. Okay, it's not forgetting. It's from my point of view now that I am seeing this in a cold site, it's lack of experience. So at that time, so we didn't figure out that. However, I have seen another systems, cooling water systems. It was a cooling water system that they have a similar problem. They have a couple of condensers, okay, a couple of condensers, very quite big condensers, and they have a bad distribution of water in that condenser because the arrangement was like this, okay. And then what they did to try to control the system is they closing the valve manually of one of the systems to get more water into the other condenser.
Okay.
And I say, okay, so this is, and this is what I realized. So this is a bad design. If you are looking for a very good distribution, we have to do something. And then we face that in the train C. I say we have the similar situation for different systems. And then this is the reason I am talking about fluid, so not talking about gas or liquid. So what we need to do or to guarantee is a good distribution of the system. Because when we run simulation, the simulation will tell us according how do you have the return in the case of cooling water, how is the arrangement of the return. It will tell you what is the distribution. It is fine, point of the simulation. But when you go to the reality, the distribution is not like that. Then we need to do something like this to improve the flow distribution of this kind of system. Not only in that case, but in other cases as well. So you go to all plants or all refineries that still deal with a cooling water system for the condensers and coolers. So you will see a lot of arrangement like that. And then and then when you start to talk to the operators, they will start to tell you what the problem, what distribution problem they have.
Okay.
And
Okay.
it's a matter of design. Okay, so it's a matter of design, and then we have to improve the design.
Okay.
Sometimes we as a process engineers, so we need to go into the piping as well.
Right.
Okay.
Yeah, sir. Got it. Thank you.
Welcome. Thank you. There was a question. Can you share this PowerPoint for future reference by mail? Yes, we will share the PowerPoint with all the attendees afterwards. So you will receive it. How many flare headers can be connected in a single flare stack?
That depends on the capacity. So you have several issues in here. One is the capacity of the flare. The second one is the coincidence of the scenarios of these flares. So you have to, first of all, what you have to do is to analyze and to evaluate the scenarios that you have for any, in this case, for any train, for any piece of equipment. What scenario is the one that is giving you the most or the higher flow rate? According to this, higher flow rate is when you size the flare header and the flare itself. And then the flare, you don't normally you don't set the flare for the maximum capacity of this. You mostly, so you talk to the flare a manufacturer, and the flare manufacturer most of the time they have flare for a let's say for capacities. They don't tailor-made a flare for you for your plant. So they say, okay, you want, what is the capacity of your plant? 30,000 barrels per day. Okay, for 30,000 barrels per day, So the flare is this, what you need, according to the capacity of your plant. Okay, and then most of the time, so you go for a flare with a higher capacity than the flow rate you, let's say, it is required to be relieved from your safety valves and the depressurized system. Okay, and then this is the, let's say, the gap that you have to play with the flare capacity, and then you can see how many flare can be installed in that case. In the case of ground flare, is a little bit more easy because the ground flare is divided into sub burners, let's say. You have a main header that is the inlet, but you have several burners, and then you can when you purchase the ground flare, so you purchase it with spares or with not with spare, with places to allocate for another subheader for burners. Okay, and then when you see, you may have maybe for the capacity you need 4 subheader for burner, but you talk to your flare manufacturer and you say, okay, I would like to, I am thinking in an expansion, I will need more capacity, and then he can leave 3 or 4 more spaces to allocate for another burners. So for ground flare, it's more easy. For elevated flare, so it's not that easy.
Thank you. Then there is one more question from option. If I understand well, for emergency cases, it is better to release the pressure of DC3 to a separated header to prevent overload to flare header system.
Can you say again?
If I understand well, for emergency cases, it is better to release the pressure of DC3 to a separated header to prevent overload to flare header system.
Not necessarily. Not necessarily. I'm not sure if the question is talking about this system or the other one that includes the DC2.
I think it is this one.
I think it's this one, because this is our proposal was this. So this unit, because of the temperature and the material the selection of materials, so to get a dedicated flare header for that unit, not to use the existing one. But the reason was not capacity. The reason was a material selection, that this system may fail when facing temperature far below -20. I'm not sure if this is the question.
Oh, I think it was. Yeah. Thank you.
But however, be aware of this, because I have another case. So be aware when you run simulations for this kind of system, because I have been auditing a technical audit for one DC2 unit, and then in the flare system, they say that somewhere in here, let's say, they change from stainless steel to carbon steel impact test. And then the knockout drum that was somewhere there and the flare was selected from that material. And then they say, well, from 200 meters from here to there, you change the material. I say, hey, why do you do that? No, because we run a simulation, and the simulation say that the temperature in here, well, according to the atmospheric temperature, etc., etc., etc. I'll say, okay, but are you sure that at 200 meters you will have this temperature change? Because it's a result from a simulator, and the simulator is giving you, let's say, some ideas of what is going on. But the reality is saying anything different. And then the recommendation in that system is, no, forget about the carbon steel impact test. Design everything for stainless steel. And then they say, well, but it costs more money, blah, blah, blah. Okay, but we're talking about safety. We're talking here about anything else. If you want to do the things well, do it well up to the end. Because the simulator can give you, because it isn't the reality. The reality is that the environmental temperature is very, for example, in countries that you live in Denmark, it's very cold in winter and very hot in summer. For the countries as ours in Venezuela, we don't have this temperature change. So, and then you have to size everything for a very hot temperature. And I think that in places like India and like Pakistan, that is very hot places as well, they do the same thing. You don't think about lower temperature, you think about higher temperature. Higher temperature is another problem, but lower temperature is only seen sometimes at night, but at night it's not as let's say, as critical as, for example, in people like in countries like Russia, in countries like Canada, and things like that. Morning. Okay, so we need to think about that and to use our common sense, and then to don't get because the simulator are giving us one let's say one idea of what is going on, one trend, one tendency, and then but the reality is different because when you try to reproduce the plant in operation with the simulation model you have, you will never get that because the reality is different. Okay.
Perfect. Thank you. That's a very good point. Thank you, Mr. Wilfredo. Any other questions that anyone might have? If not, then we can move on to.
Humzaa, I have seen that somebody else was asking for my LinkedIn link.
Oh yes.
I don't know
very
if you
good
can
point.
supply it to. You can supply it for them by email.
I will right after the webinar, when I send out the certificate to all of you with the PowerPoint, I'll also share Mr. Wilfredo's LinkedIn link as well, so you can click on it and connect with him there as well.
Perfect.
So I will do that. I'll do it right after the workshop. Great. Then about the next steps after the workshop. Well, firstly, thank you to everyone that joined in today on this Sunday morning. And we hope that you got something out of the webinar. Now I will send out the certificates to all of the attendees so you all can have a copy and show your attendance if required. At the same time, I'll also send you a link for evaluation for the webinar. And we would really appreciate it if you could go in and tell us about how you thought the webinar was, so that we can use it to improve our future webinars. And lastly, I'll also share the PowerPoint and also the other information, and also Mr. Wilfredo's LinkedIn profile link in the email. And also I'll also share the recording of the webinar with all of you, so you all can go in and watch it again if you wish. The video will be uploaded on our YouTube channel as well, so you can also go there and watch it. Is there something you would like to say before we log off, Mr. Wilfredo?
Yes, so normally I am open to any question you have, point of view, technical, personal, whatever. So I am now, if you have my link, my LinkedIn connections, so we can connect over there. Any consultation you have, any question you have, anything, I am here to help everyone. I am happy to do that.
Perfect. Thank you. That's very kind of you. And please do connect with him and do ask him any questions that you guys may have. Like I said in the beginning, he has more than 30 years of actual experience of working in the industry. So I highly suggest that you make use of this opportunity. So once again, thank you so very much, Wilfredo. And
okay.
Well, then I would just like to say to everyone, thank you very much for joining us today, for taking time out of your Sunday to come and listen to Mr. Wilfredo speak about the safety design. And a huge thank you to you, Mr. Wilfredo, for joining us and for sharing your knowledge and for preparing the slides. I believe I speak for everyone when I say that we all are truly grateful to have you as a guest speaker today on the platform. If you have not done so already, then do remember to go to our website and become a free member, because we have a lot more webinars planned up for the future. And if you are a member, you will be the first one to know when they are being held, and you will get an opportunity to sign up as soon as we go live with them. So thank you once again, and I'm very much looking forward to seeing all of you once again at our future webinars as well. And I hope you all have a great Sunday ahead. Thank you.
Okay, bye-bye.
Thank you. Bye-bye. Thank you.